Okay, learners, we are coming to the last part of the second chapter, the structure of atom. We are discussing electronic configuration of elements. In fact, well, whatever the elements that we have discovered and that which are artificially produced, we'll be trying to understand how the electronic configuration is related to the periodic table, and what are some like special elements where the electronic configuration is not normal. There's some exception in writing that. Say, for example, this is the modern periodic table, and it's been divided into S block, P block, D block, and F block elements at the bottom. We have written electronic configuration of hydrogen, helium, then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, up to argon. We have written the electronic configuration. Now comes potassium. What is the electronic configuration of potassium? In fact, by looking at the position of the element, you will be able to determine what will be the electronic configuration, or at least what would be the electrons in the valence shell, or the outermost shell, or the shell with the highest principal number. What are the electrons in the valence shell? Not the core shells. Core shells are where the electrons are completely, the subshells have completely filled electrons. The quota is full there. So the electronic configuration of potassium will be like it's in the fourth period, first, second, third, fourth. So the fourth shell is getting started filled from potassium up to argon. The third shell has been filled. So it's like 1s. For hydrogen it will be 1s, then 1s2, then 2s. This and this are filled up. So 1s2, then 2s. For lithium is 2, 1s2 to 2s1, then for this 2s2. Then comes for boron the last electron, 2p6, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. That means 2p is again filled up. For sodium it will be whatever you have written for hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, those will be filled up, right? So we write neon, electronic configuration of neon, and then we write now 3s will be 3s subshell will fill up. So 3s1, for this 3s2, because it's not, for those elements which are in third period or in the third row, the 3s and 3p will be filled up. 3s and 3p, 3s, then comes 3p. Here the 3p1 will fill up for aluminium. The last electron will be in 3p1. For silicon it will be 3p2, 3p3, 3p4, chlorine 3p5. For argon it will be 3p6. The 3p6 electrons are filled up in argon. Okay, so what about calcium? Calcium will be, we will write the electronic configuration of argon, for which 3p subshell is filled up, completely filled up. Those will be co-electrons for calcium. Now 4s subshell will fill up. 4s1 for potassium, and for it 4s2, right? So up to calcium it's okay. Now after calcium, what comes is we'll finding a new group of elements for which d orbitals are filled up, because according to Aufbau principle, after 1s 2s, after 1s 2s 2s 2p, 1s, then 2s 2p, 3s 3p, 3s 3p, then comes 4s, right? 4s, and after 4s 4p doesn't come. In between, what comes is 3d. Before filling up 4p orbitals or 4p subshell, you need to fill up 3d, okay? Because 4s and 3d, okay, before filling up 4p, you have to fill up the 3d first. So let's see why not 4p first? The question is, why not 4p first? Why we are filling 3d first? In case of 4p, what is the what is the value of n plus? How will we find that which will have lower energy? Here n plus L value is n, the value of n principal quantum number is 4, and p means 0, 1. The azimuthal quantum number is 1. So 4 plus 1 is what? It is 5. The n plus L value is 5 here. In 3D, the n plus n value will be, the sum of the principal quantum number and the azimuthal quantum number will be 3 plus 2. Here, d means the value of L is 2, 3 plus 5. That means both are having the value of n plus the value of n plus n, or sum of n plus L, same. But since this is having the principal quantum number less, so 3D orbital is having less energy than 4p orbital. So instead of for before filling up the 4p orbitals, we need to fill up the 3D orbital first. So there comes the elements in which the 3D orbitals are filled up. The d orbitals, they can accommodate a maximum of 10 electrons. That means there will be 10 elements. So here to here, scandium to zinc, in d orbitals, there will be 10 elements in which the d orbitals are filled up progressively. So the first element is scandium and its configuration will be up to argon. Then after writing the configuration of argon, it will be 4s. This 2 is filled up, 4s2. Then comes 3d1. For titanium, it will 3d2. Similarly for vanadium, it 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Right? So up to zinc, the d orbital will be completing. Then come for gallium, it will be after writing 3d10, it will be like it's 4 shell was filling up, 4p1 for this, 4p2, 4p3, 4p4, 4p5, and 4p6 in krypton. The 4p subshell will be completely filled up. Right? Okay, but there is an exception in the two elements have a very interesting electronic configuration, especially the valence electrons and the electrons, how they are kept and how they are filled is the chromium and copper. We will try to understand the electronic configuration of chromium and copper, which is little bit exceptional because of some reason. Right? For normally, if you are not taught this chapter, this topic, and you are told that you need to write the electronic configuration of chromium, how will you write? You will write like this. You will write the electronic configuration of argon that you know. Then we are not knowing the electronic. We need to number of electrons, right? So we can find it from here. Up to argon is 18. Then it's 19, 20, 21, 22, 23, 24. So its atomic number is 24. You need to fill up 24 electrons. Up to argon is 18, 19, 20, then 24. So 4s2 is filled up. Then will come 3d. So 18 plus 19, 20, 24. This is the way you would have written the electronic configuration of chromium. 4s2, 3d4. 4s2 up to here, 4s2, 3d1, 3d2, 3d3, 3d4. So 3d4. Alright. Like for scandium, how will you write? You will write argon, then then you write 4s2, then 3d1. For titanium, how will you write? Argon, 4s2, then you will write 3d2. For vanadium, how will you write? For argon, 4s2, 3d3. So obviously for chromium, you will write 4s2, 3d4. But now, what is the exception about this is that instead of writing 3d4, for the correct electronic configuration of chromium is 3d5. How is this done? One electron from the 4s orbital or 4s subshell is transferred to the d orbital. It becomes d5. The electron will be same. Is 2 plus 4 is 6. This is 1 plus 5 will be 6. But the thing is happening is one electron shifted to the d orbital, to d orbital. Why? Because the d orbital, the half-fill orbital, the general rule is the half-fill orbital or the full-fill orbitals have extra stability. They have lesser energy. So in order to attain, so everybody in the universe, everybody every object in the universe tries to have less energy, right? So this is more stable. Less energy means more stability. So the half-filled d orbitals are more stable. So as for example, see here, P3, P6. This is half-filled P. This is full-filled P. half fill D, full fill D, half fill F, full fill F orbitals, right? So the half fill orbital P3 or P6, D5 or D10. This is completely filled d orbital. This is half filled d orbital. So half filled d orbitals have extra stability. So so the element or atom tries to have that configuration, which makes it extra stable with lesser energy. So that's why the configuration of chromium is, instead of 4s2 3d4, it's 4s1 3d5. In the same way, the configuration of copper is, instead of 4s1 4s2 3d9, here the copper 4s2 3d9, it's 4s1 3d10. 4s1 3, one electron is shifted here, it's 4s1 3d10. That will be the correct electronic configuration of copper. Copper, the atomic number copper is 29. Actually, instead of writing argon, I'm writing the complete electronic configuration, not using the symbol of argon. So it will be like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d9. This is incorrect. It should be 4s1, 3d10. This is the correct electronic configuration of copper. Yes, I hope you understand this. Now, the next interesting thing is, after rubidium, in rubidium, the 4s subshell, 5s subshell starts filling 5s, 5s, then comes 5p. Before 5p, there will be 4d. Like before 4p, there was 3d. So before 5p, there will be 4d. 4d electrons will fill up here, up to xenon. Up to xenon, the 5p subshells will completely fill up to xenon. Now comes cesium and barium. Cesium here, the sixth shell will start getting filled up. 6s1, 6s2. Then comes the lanthanides. Lanthanides. Before lanthanides, what is more interesting is that before filling this, after 6s, it will be 4 or 5d, right? Before filling up 5d, there's one more group of elements which needs to be filled up, called 4f elements. Those are called lanthanides, because it starts from lanthanum. It comes just before lanthanum, so it's lanthanides. Cerium, promethium, something like that. The elements in this group, in this period, from here 58 to 71, atomic number 71. So these are called lanthanides, in which the 4f orbitals are filled up. Similarly, after filling up this and these two elements, actinides comes. Before filling up 7s, before filling up 7p or 5d comes, or 6d comes the 5 elements. For the 5 elements, which start from atomic number 90, then uranium, americium, curium. These elements are called actinides. Here, these are after uranium. The elements are short-lived. They are artificially produced. Remember this: after atomic number 92 up to 103 or 170, whatever elements we have discovered, all the elements are not naturally found. They are artificially produced. Okay, I hope that you have understood something about this. The electronic configuration completed. With this, we come to the end of this chapter. We will try to solve some numerical questions and some concept-based questions from the textbook as well as from examinations.